Hello again, I'm Nix, and the topic for today's video is solving the valid mountain array problem on the LeetCode website. As always, doing this problem in C++ and giving you a detailed explanation of the entire process, from the planning out of the algorithm to the actual coding to the analysis of said code, where we go over time complexity, space complexity, and looking at LeetCode rankings. If that sounds good to you, then stay tuned. Welcome back. Now, this problem essentially is an exercise in being able to deal with a few test cases, as you'll see when we start planning out the algorithm. But first things first, let's go over the problem and make sure we all understand it. So, we're given an array of integers named after a pirate sound. Return true if and only if it is a valid mountain array. Okay, what's a valid mountain array? Recall that array is a mountain array if and only if it fulfills some conditions here. So it has to be at a length at least equal to 3 or more, and we have to have an index somewhere within the array such that the first value is less than the second value, and so on and so forth up until the value at that index, and then after that index the values slowly go down. So we're increasing to the index, and after we get to the index we're decreasing, as this handy dandy picture shows. So a mountain array is going to only go up to some point in the array, and then after that it only goes down. And this example here, it goes up, but not strictly. There's a value tie somewhere here, and then it goes down. So the path that this array forms has to be one simple mountain. It can't have plateaus, it can't go down and then up, it can't go down and up multiple times. Nope. It goes up and then goes down only. Right? We have some examples here. This is automatically going to be false because it doesn't fulfill this condition. This one, while 3 goes up to 5, 5 to 5 is a plateau, so it's not strictly increasing and then decreasing, so it's false. But this one, from 0 to 3, it goes up, and then from 3 to 2 go down, 2 to 1 we go down. We make a little caret. It's a nice, simple one-peak mountain, so true. Okay. Constraints, we could potentially be given an array that is less than the minimum amount required in terms of length, and various positive values. So with that, these conditions here kind of clue us in on the key things that we need to pay attention to in order to solve the problem. We need to make sure that the length is above the minimum requirement. So that's one edge case we need to make sure we deal with. And then essentially the major thing we need to look for is handled in this statement right here. We need to go through the array, and as we go through the array, we need to make sure that we are first increasing up to a point. And then wherever that point is, after that, we need to make sure we're only decreasing. That indicates that we're going to need to use two loops, two separate ones. The first loop will handle essentially the uphill climb, and the second one will handle the downhill climb. Now, to traverse through the array, we're going to need a variable that tracks our position in the array. And as soon as it gets to this peak here, we need to stop this first for loop and then use that variable's position to then start that second loop and make sure it's decreasing from there. So to help crystallize a little bit more on what this code is going to need to be able to handle, let's go over a couple of test cases. And I need to throw my cat outside of my room because he's starting to get chatty. These are the test cases that I used when I was constructing the algorithm. The first two here are fairly typical. We have a case that should end up being true, being a valid mountain array. It goes up, then it goes down always, so good. This one, a typical negative case where we don't technically have a peak, we have a plateau, which doesn't fulfill the condition. But it's these two cases here that are more of edge cases. In this first array, we have an array that is strictly increasing all the way to its end. It has an uphill climb, but never a downhill climb. This array is the reverse of that. It starts at the peak and only goes down. It never goes through an uphill climb and only has the nice, easy downhill part. So the algorithm that is being built needs to be able to handle these two extremes. The first algorithm here is fairly easy to be able to get a catch for. After the first for loop happens, where you're making sure that you're on an uphill climb, you can create an if statement that checks whether or not you're at the end of the array at this point. If you are, then you know it can't be a valid mountain array because you've only done the uphill part, not the downhill part. So at that point, you can just go ahead and report false. This case, however, is going to result in that first for loop never actually triggering, because at no point do you ever get a positive comparison that the values are increasing. But when the second for loop occurs, it's going to go through and see, hey, everything is decreasing as it should for my part of the algorithm, so everything is awesome, right? We're good. No. If you make it through the second loop, you'd be good if and only if the first loop actually triggered, and at some point, even if it was just for one step, we went uphill. So to be able to handle this test case, in addition to the variable that walks the path and helps us figure out whether this is going to be increasing and decreasing, we also need a second variable that is going to serve as a switch and let us know that at some point in time the first loop did trigger and we went uphill. So what are the parts of this algorithm here? We need two variables. We need a variable that walks the path, that's going to be an integer, and we need a variable that is going to serve as a switch. So we need a boolean to ensure that we went uphill at some point before we check and see that we went downhill. Then we need some loops to occur. The first for loop is going to handle the uphill climb. It's going to start at the beginning of the array and go until the array stops increasing. At that point in time, our variable that walks the path is going to be at the position of the peak. Then we need to do a check to make sure we're not at the end of the array. And we also need to do a check to see that that first loop did indeed happen at least once, so that we did go uphill. If either of those conditions are false, we can just return false and it's not a valid mountain array. Then we go through the second for loop. That second for loop is going to handle the downhill climb and start from wherever the variable that walks the path is at and goes to the end of the array. And that for loop is checking that all of the variables are strictly decreasing at that stage. And if we make it past all of those checks, in addition to the check of having the array be at minimum 3 long, then if we make it through all of that, then we can report true. Okay, let's get to coding everything I just said. Here are the two variables that I was talking about. So we have the variable that travels the path, which in an attempt to be amusing, I named hiker, and I set that to 1, which will become apparent soon. And the second variable is one to record whether or not it starts as an uphill climb. So I named this Boolean variable going uphill, and I initially set it to false. Next up is handling the test case of the minimum length the array should be in order to fulfill the condition. So if array.size is less than 3, we can just return false. Here's the first for loop that handles the uphill climb. So for this one, we want to set the index to 1, and the reason for this is because in the conditions within the loop, I'm looking backwards relative to my position. So in order to make sure that I minus 1 is still within the boundaries of valid index numbers, I need to start off this index at 1 so that 1 minus 1 equals 0 and not negative 1, which is out of boundaries at the start. So this is equal to 1, and that is also why hiker is equal to 1, because I want the starting place and the hiker to be at the same position. The for loop will go until the index is at the end of the array, or if it breaks early, and of course increments up as such. Now looking at the if-else statements here, the comparison is if the previous value is less than the current value, so in other words, we're going up, then increment the hiker's position. So it's going to hike up the hill. In addition to that, if the going uphill boolean is initially set to false, which it is, then if this if statement has triggered, we're going to switch that to true because we have indeed gone uphill. So this is going to trigger as long as we keep climbing up. And the hiker is going to continue moving along until this condition is not true, or we've reached the end of the array. If this condition isn't fulfilled, we're going to break out of this for loop and freeze the hiker where its current position is. Alright, at this point, after the first part of the hiker's journey is complete, the first for loop has run or been skipped in some cases. This is when our hiker wants to take a break, take a bit of time to rest and meditate and drink some water. In other words, this is the point in the code where we do some checks for some edge cases cropping up. So if at this point, after this for loop has run, our hiker is at the end of the array, then it's not a mountain array and we need to return false. This if condition will also trigger with this or operator here if the going uphill boolean at this stage is still set to false. At no point have we ever gone uphill first, which is what we need to do. So we can check that condition here and also return false. So if either of these things is true, not a mountain array, return that result. Next is the second loop. This is the one that handles the downhill climb. And for this one, the index is going to start at whatever the hiker's position is. Wherever he was frozen after this for loop is where the second one is going to start. Again, it's going to go until the end of the array and has some if-else conditions here. Again, we're looking at the previous index and seeing if it's bigger than the value at our current index. If it is, the hiker continues his journey by incrementing up the integer. If that condition is not true, either we go back to be going uphill for a little bit, or we're hitting a plateau where the values are the same. Well, not a mountain array at that point, so we return false. Finally, if at this point, going through all of this, making sure that we have enough of a path to walk, going through the first uphill climb, and then during the meditation and water break here, checking to see if we have any test cases we need to eliminate, then going for our downhill climb, if we've gotten through all of that, then we have traversed a valid mountain array and we get to return true. This entire code should handle all of the test cases and shouldn't have any errors. So let me prove that to myself and to the viewers. Finished, false, false, that's good. Submit. Pending. Judging. Accepted. Woohoo! Alright, now let's go over some time and space complexity before we go through the LeetCode rankings. In terms of space complexity, at no point in time am I ever creating another container, making new vectors, stacks, queues, arrays, whatever. I'm just making some small constant space variables, and then I'm walking through the array. So this algorithm should have pretty much constant space utilage. And that means that the big O for space complexity should be big O of 1. In terms of time complexity, we have this for loop that's unnested and this for loop that's unnested. So the combination of those two arrays will go through the entire array. Everything within those for loops is constant time use. So this is going to be an algorithm that has a big O of n time complexity, where n is the size of the input array. With that, let's see where I am in the LeetCode rankings. Okay. Tightly bound runtime. And this distribution, to me, indicates that there's probably only one kind of general time complexity case. So if I rerun this code, I'm probably going to ping pong around here. It did not register my memory usage. But this is an extraordinarily tight memory usage here. I'm going to try to rerun this and see if it actually gives me a value, because I want a "you are here" indicator on my memory usage. So I'm going to resubmit this. Didn't change anything. Judging, accepted. And, yep, see, ping-ponged up here. Hey, yay, I get the "you are here" sign. So with such a tight spread here, that also kind of clues you in that there aren't any big variations in the general type of solution for this code. There isn't something that would have a big O of 1 constant time and then a big O of n memory usage, then a big O of like log n memory usage that can be seen in terms of different distributions. The various solutions all have pretty much the same type of memory usage, that being constant. That was the valid mountain array problem on the LeetCode website. I hope this video was useful for you in some way, and as always, I will wish you happy coding and have a nice day.